Greetings. My name is Dr. Peter D'Antonio, Director of Research at REDI Acoustics. Thank you very much for viewing the Room Acoustics Design and Optimization presentation. We would like to share our research in developing an iterative optimization palette of software tools to optimize the design of critical listening rooms of any shape. Following the sale of RPG diffuser systems in 2017, I wanted to extend my research in optimizing the design of critical listening rooms, which we started with the Room Sizer and Room Optimizer 3 decades ago, to include non-cuboid spaces. I began collaborating with D'Antonio and Rinaldi Petrolli, then an intern at WSDG. The result was a wave-based iterative optimization software program called the Non-Cuboid Iterative Room Optimizer, or NERO, in 2020. Its success resulted in founding an independent research and educational development initiative software company called REDI Acoustics. Since 2020, we've expanded our staff, published a couple of papers, and the number of optimization tools to address other critical parts of room acoustic design, which we will describe today. I will begin with a brief introduction, followed by a detailed description of the current software by Rinaldi Petrolli. The sound that we perceive in a room is influenced by the interaction of several factors: the room size, shape, and the mass stiffness of its boundary surfaces, as well as the placement of spectral, spatial, and temporal characteristics of the loudspeakers, and the location of the listeners. At high and mid frequencies, we hear predominantly the direct sound, which may potentially be corrupted by comb filtering, resulting from delayed reflections from adjacent walls, ceilings, floors, and console. At frequencies below the room transition frequency, modal resonances and their temporal decay in the room begin to dominate the character of the sound. REDI has developed a palette of iterative optimization software tools that minimize all forms of potential acoustical distortion resulting from this interaction to create a room that is neutral. By removing acoustical signatures of the room, the mix can be transferable to other listening environments. This idea is embodied in the slogan, "If you can't take the room out of the mix, you can't take the mix out of the room." The palette includes the Non-Cuboid Iterative Room Optimizer, NERO, the Room Optimizer for Cuboid Spaces, ROX, the Treatment Optimizer for Room Acoustics, TORA, and the Acoustical Treatment Calculator, all of which will be described in this presentation. The potential forms of acoustical distortion include room modes, SBIR, comb filtering, and pore diffusion. Because the source location determines which modes are excited, and the listener location determines which modes are heard, we must simultaneously optimize the geometry and the locations of the speakers and listeners. Now, the speaker boundary interference response results from the coherent interference between loudspeakers and the adjacent room boundaries, which also depends on speaker placement. It can be improved by adding acoustical treatment and flush mounting the monitor speakers. Comb filtering results from coherent interference between a direct sound and an isolated reflection that creates interference patterns in the frequency response. It can be controlled with broad bandwidth absorption or reflection from a surface 8 or more times the wavelength of the lowest cancellation frequency. Finally, pore diffusion results from a non-mixing environment or excessive absorption. It can be controlled using sound diffusive surfaces and ensuring that the diffuse reflections arrive at the listening position from angles with low interaural cross-correlation to maximize the sense of envelopment. With all of the metrics considered, the goal is to minimize the modal and SBIR interference and recreate the temporal signature of a well-designed performance space with an ITD, or initial time delay, followed by a diffuse sound field. To do so, we utilize the 4 following metrics. First, we strive to create a flat, controlled low-frequency response with minimal spatial variation around the mix position. Here we analyze the narrowband frequency response at the mix position and how it varies in a grid of points around the center position. Then we check the temporal decay to ensure that the decay times at low frequencies are within the recommended thresholds to avoid audible modal effects. To properly address the potential nonlinear behavior of room modes, we use a frequency domain approach to estimate reverberation time values. Next, we move up the spectrum and adjust the traditional mid and high frequency reverberation time to comply with the standard recommended values. Lastly, we create a reflection-free zone with reflection levels below the thresholds of perception and a temporally dense diffuse field zone with a minimum of strong isolated reflections. For a given geometry, the difficult challenge is to find the optimal sweet spot at all frequencies in a minefield of pressure peaks and valleys for the speakers, listeners, and the acoustical treatment. To simultaneously optimize all of the objective measures, we use a multi-objective evolutionary search algorithm to iteratively find the best metric combination where no metric benefits at the expense of another. To answer the challenge, we have developed a palette of software tools, including Nero, ROX, and Tora, which optimize the acoustical design within the architectural and aesthetic constraints and the accessible areas for speakers, listeners, and acoustical treatment. We offer these optimization tools as a collaborative design service to the design team. We begin the collaboration with a kickoff meeting to obtain the room drawings and learn the design requirements, architectural constraints, accessible areas, and the desired speakers and subwoofers. We then optimize the room acoustic design with our algorithms and provide a detailed written report with the design firm's identity. After that, minor adjustments can be made to accommodate any unexpected changes or adjustments. I would like to introduce Rinaldi Petrolli, who will describe in further detail the inner workings of our optimization framework, go through a sample report, and provide a few project examples.
All right, Peter, thanks for the introduction. I'll start with the basics. So first I'll talk a bit about dimensional analysis of cuboid rooms, which is where many low-frequency optimization methodologies start. And the beauty of it is that with a straightforward equation, we can know the frequencies of the discrete room modes happening at the room length, width, and height, which will be the most significant contributors to what actually happens in the modal range. And this equation tells us the resonant frequency of the modes, but tells us very little about the amplitudes, because that is very dependent on the positions of both sources and listeners. To illustrate this, I will show a very simple example. Here we have a cuboid room with rigid walls, where I have a speaker in one of the room corners and a microphone on the opposite diagonal corner. So it means that we are simultaneously exciting and hearing all the modes. The blue curve represents the simulated frequency response at the microphone position, and the piano roll below shows the modal frequencies predicted with the simple modal formula I've described earlier. And here we can see that the peaks of the frequency response line up perfectly with the frequencies predicted by that simple formula. Now, if we take that same case, but consider that we don't have rigid walls, meaning that the walls are compliant and absorb part of the energy, we will have the curve below. Here we are adding a real admittance of 0.02, which doesn't have an imaginary part, and that means that it doesn't change the phase, but still has a significant impact on the amplitude of the peaks and dips in the response. Now let's keep on making it more realistic by maintaining the compliant walls, but now bring the source out of the corner into the front third of the room, which increases the misalignment between the pure modal frequencies and the response that we are simulating. Finally, if we bring our microphone to a typical receiving position at 30 degrees with the listener, we will see another significant change in the frequency response, again showing the strong relationship between the perceived modal response and the positions of the sources and the listeners. In more complex projects, it's important to model non-cuboid rooms accurately and go beyond their dimensions to truly understand the frequency response. We also need to consider the placement of speakers and listeners, as well as the acoustic treatments and their properties, so we can estimate their impedance. All of this is critical information, and the geometric modeling is a major component of the process, one that we spend a lot of time on because it directly impacts the simulation results. With that in mind, let's dive into our framework. To start, I would like to refer to this graph, which illustrates how sound behaves within a room across the audible spectrum. So in the first region, we have the pressure zone, which occurs below the room's first resonance, and following that, we have the normal mode zone, which is where we apply wave-based acoustics and account for the surface impedances for greater accuracy at low frequencies. Beyond that, we entered regions dominated by diffusion, reflection, and diffraction, where we shift to geometrical acoustics by using methods like ray tracing and the image source model instead of wave-based acoustics. The first simulation technique we'll discuss is the finite element method, which is a very robust approach, especially at low frequencies. To apply it, we need to know a lot of details about the room, like the source and receiver positions, have a detailed 3D model of the space, and also know the source directivity. We also need to define the maximum frequency of analysis, which will determine the size of the mesh elements that are placed across the room's 2D surfaces and also within its 3D volume. And as we can see in the bottom center graph, we also mesh the inner room domain, in this case the air. Here we need to account for the surface impedances of all the room surfaces and acoustic treatments, as well as the fluid properties, which is air in this case, but could also represent treatments like floating acoustic clouds, which are very common in control rooms. Once we've meshed the room, we can calculate the pressure at all the meshed elements and then interpolate the pressure at any point within the room. This is a wave-based frequency domain solution, but we can also derive the time response by applying an inverse Fourier transform with the appropriate signal processing. While this method is computationally demanding due to the requirement for matrix inversion, especially at higher frequencies, the precision at low frequencies is really good. This is because we are using surface impedances to represent the room materials, meaning that we are accounting for the changes in phase occurring at the boundaries, which is a crucial factor for the proper representation of low frequency effects. The second method I would like to discuss is the image source method, which is the technique used in the room sizer and room optimizer programs that RPG sold years ago for optimizing rectangular rooms. It requires the positions of both the source and the receiver, along with the room surfaces, and it can account for surface absorption and source directivity. The method is conceptually similar to the traditional technique where you stand by a wall with a mirror to locate the point where you can see the speaker, which will represent the specular reflection point at that wall. The image source method extends this by calculating multiple reflections across all surfaces for multiple orders of reflection. A first-order reflection involves just one reflection point, while a second-order reflection involves two, and so on. The main advantage of this method is its speed. It's incredibly fast, especially for cuboid rooms, and when we are dealing with non-cuboid rooms, the visibility test that determines whether a reflection will reach or not the receiver becomes computationally expensive at higher reflection orders, so in those cases it's not always fast, but still, performing high-order calculations with this method can be quite accurate for empty rooms even if they are non-cuboid. However, when we introduce treatments or compliant boundaries, the method loses precision at low frequencies because it doesn't account for complex impedance or phase changes, and it also neglects any scattering effects. Despite these limitations, it's incredibly effective for quickly and precisely identifying reflection points, which is where we mainly use it. On the left, we can see a reflectogram, which shows the timing of each reflection and their amplitude, factoring in surface absorption and source directivity. This helps us evaluate the early reflections arriving within the reflection-free zone and whether they are sufficiently attenuated or not. Lastly, we have stochastic ray tracing, which is probably the most commonly used of the three methods in acoustics overall. This technique actually originates from optics and has been adapted for acoustics, and is primarily used for larger spaces like concert halls, as demonstrated here by the billiard ball animation. The concept is that we project multiple rays from the sources, which bounce around the room. We then track how many rays and from which directions reach our listening positions. By analyzing the number of hits, their directions, and their intensities, we can estimate the impulse response at the receiving position and ultimately obtain the time domain solution. To perform this process, we need a lot of information about the room, including its geometry, surface absorption, and scattering. Additionally, the source directivity is crucial. If we want to include a more realistic experience, we also need to factor in the head-related transfer function of the listener. In many ways, this method functions similarly to the image source method, where we generate time echograms across different frequency bands, and then these frequency bands can be combined to form a full band representation of the acoustic behavior of the room. Using this time echogram, we can transform the data into an actual impulse response, which can be achieved through minimum phase reconstruction techniques, although this can introduce some artifacts into the simulated response. However, the echogram also allows us to estimate the reverberation time, which is a critical parameter in acoustical analysis and probably the most popular one. One important caveat here is that this method was designed primarily for larger spaces, so its limitations become more apparent in smaller rooms, particularly at lower frequencies. This is because it doesn't fully capture phase relationships due to not using complex impedances, and additionally in smaller rooms, both the sources and receiver are often positioned close to adjacent boundaries, further reducing the precision of the results at lower frequencies. Finally, with the different parts of the spectrum simulated using their respective techniques, we can now combine them. We first take the frequency domain solution from the FEM at low frequencies, filter, and then transform it into the time domain solution. And then we take the time domain response from the ray tracing, filter it, and combine it with the response from the FEM modeling. By merging these two approaches, we obtain a full band frequency response, and the crossover frequency between these two methods can be adjusted either higher or lower depending on the objectives and the computational limitations. This is the current state-of-the-art technology for achieving full band room acoustic simulations. This graph illustrates the expected accuracy of the acoustic simulations using this framework. Here we are comparing the frequency responses and reverberation times of a simulation with the measurements from a real room using actual admittances and absorptions. While it's not a perfect match at every individual frequency down to the hertz level, the general behavior of the curve aligns quite well. This is especially valuable for smaller critical listening rooms, where compliance with strict standards is essential. It's generally much more cost-effective to address potential issues during the project phase, where simulation allows for easy adjustments. Once the room is built and everything is in place after payments have been made, making changes becomes far more expensive and time-consuming and frustrating for all the parties involved. In summary, the simulation framework allows us to take a precise snapshot of a room, examining various parameters simultaneously and showing us whether we have a good or bad solution. This is a crucial aspect for projects with many variables, like optimizing non-cuboid rooms and many acoustical treatments, where trying to achieve good results for 2, 3, or even 4 simultaneous parameters through manual iteration can be incredibly time-consuming. This is where the optimization process comes in. A fine-tuned optimization engine will enable us to automatically generate and evaluate numerous configurations, searching through variable and parameters to find the optimal solution for every case. From this idea, the non-cuboid iterative room optimizer, or NIRO for short, was developed. NIRO is our first optimization algorithm, and it's designed to simultaneously optimize the room geometry along with the positions of listeners and sound sources. The goal here is to optimize the low frequency response and minimize the spatial deviations around the listening area, as well as reduce the early reflections arriving in the reflection-free zone. In this process, we consider all aspects of the room's design, wall positions, distances and angles between the listener and speakers, as well as source directivity. For rooms with moderate complexity, it's common to run thousands of simulations with various constraints. Manually optimizing all of these factors would be overwhelming, which makes using an optimizer the only feasible approach to ensure that all possibilities are explored. There are millions of potential configurations, and even with an experienced user, some options might be overlooked if not enough time is given. NIRO has been instrumental in helping us design rooms that we can trust, since this stage of the process is critical before moving into the next phases of acoustical design. Still in what we like to call the first phase, where the room is still empty and we are determining its dimensions and the positioning of the elements inside, we've also developed ROCs, which can be thought of as NIRO's younger brother. While NIRO is designed for non-cuboid rooms, ROCs focuses specifically on cuboid rooms, with its acronym standing for Room Optimization for Cuboid Spaces. The core idea remains the same as with NIRO. We are optimizing the room's design to achieve the best possible acoustical results at low frequencies, but since these are now cuboid rooms, we can be faster and more efficient by using some simulation shortcuts. In addition to this, since the rooms have a fixed number of surfaces, we don't need to account for reflections in the same way we do with more complex geometries. As we continue optimizing the room's basic structure in this first phase, we are setting the stage for the next steps. So once the room's geometry and positioning are finalized, we can move into treatment design and other advanced aspects of room acoustics. And now we move into the phase focused on rooms with treatments, meaning spaces with a clear design intent. At this stage, we already know how the surfaces should look and feel, as well as the available areas for all acoustic treatments. This phase applies to nearly all projects because while we might not always be able to change the room's geometry, we can almost always adjust the acoustical treatments to enhance the room's performance. So enter TORA, standing for Treatment Optimization for Room Acoustics. And this is the most complex optimization tool that we have because it takes into account 4 different metrics simultaneously. Here, we are optimizing not only the low frequency response and its spatial deviation, but also the temporal decay at low frequencies and the reverberation time at mid and high frequencies. What makes TORA particularly powerful is its ability to optimize complete sets of treatments for individual designs. In some rooms, there may be up to 15 different available treatment areas, and each one of these areas could have anywhere from 18 to 63 different treatment options, depending on the available depth and the desired appearance. This creates an enormous number of possibilities to consider, far more than we could ever evaluate manually, and this is what makes using TORA so helpful. Building on the same principles that TORA uses, we developed an auxiliary tool called the Treatment Sweeper. This tool allows us to take a very focused look at the frequency response by applying different absorption distributions to all treatments. Essentially, we take a single treatment and evaluate all the possible configurations it can have in terms of absorption. We then observe how these configurations impact all of our 4 metrics: the low frequency response, the spatial deviation, the low frequency temporal decay, and the reverberation time. The treatment sweeper is particularly useful after an optimization process because it allows us to check if any specific treatment might perform better than what was found during the initial optimization. Additionally, when a design change is introduced, whether it's a change in material design or another factor, it can help us evaluate new options and make adjustments based on the updated conditions very fast. Both TORA and the Treatment Sweeper focus primarily on optimizing acoustical treatments. In addition to using manufacturer data, they also need to independently predict the behavior of multi-layered acoustic treatments to get the surface impedance. This is a crucial tool that we use internally, and because it has proven to be so helpful in many different cases, we've developed a free app that is available to everyone. The app is called the Acoustic Treatment Calculator and is freely available on our website. It allows users to calculate the absorption characteristics and the surface impedance for a wide range of multi-layered treatments, from perforated panels to slotted panels, as well as simpler insulation panels. It has simple visualization features, making it easy to interpret and apply, and you can also download a spreadsheet with all the details and data in it. When we work with optimizing a project, the base deliverable for the architects and consultants who hire us is a comprehensive PDF report that provides detailed information on the room geometry, placement of elements, the acoustic characteristics of the treatments, and the performance across all the metrics we've discussed. The report typically starts with a simple introduction page, including a few photos and a general overview of the project, such as in this case, a control room. In addition to the PDF report, we also provide an interactive HTML report, which contains a digital interactive duplicate of everything we'll see in the PDF version. The first half of the report covers the basic information about the room setup, where everything is located and how the layout is organized. It includes overlays with the existing architectural drawings that were used to create a 3D model, ensuring alignment between the design and the acoustic simulations. We also provide detailed information on all the sources in the room, especially when working with immersive systems. For Dolby Atmos setups, we ensure that all sources are positioned and configured according to Dolby's standards and guidelines, and this is fully documented in the report. At this stage, we examine all the sources individually to ensure all of them meet Dolby Atmos parameters and guidelines. We also analyze the sources together, along with the room geometry and their positioning, to identify any reflection hotspots for each one of the sources. This allows us to ensure that the acoustic treatments are addressing those hotspots effectively, so as not to distort the perception of the source localization within the 3D acoustic space. This step is crucial in maintaining the spatial integrity of the sound field for the immersive system. We provide detailed information on all the treatments, including their location, sizes, and dimensions, along with the acoustic performance that they are designed to achieve. The report includes all the information required to understand exactly how to build the treatments, from perforation patterns and spacings to insulation type and density. So if you or your team wants and knows how to build them, this will provide all the acoustical details needed to do so. We can also incorporate commercial products or a mix of custom and commercial solutions to achieve the best possible outcome for the room. The report clearly outlines how much of each type of absorption is needed and where it should be placed, providing this information in a really simple and direct way. In the second part of the report, we dive deeper into the acoustic characteristics of the room. We analyze the reflections, particularly those within the RFC, and the focus here is on identifying early reflections that could interfere with the perception of the direct sound. We quantify their energy levels for every relevant frequency band, ensuring they are minimized to maintain the stereo precision in the listening area. Here, we also look at the mid and high frequency reverberation time and see its position in relation to the metrics set by the international standards. In this section, we also present the low frequency response and the low frequency temporal decay for multiple sources and in some cases for multiple positions within the room. This analysis is crucial in understanding how the room handles low-end energy, which often accumulates and causes issues like modal resonances. By evaluating both the frequency response and the temporal decay, we can ensure that the room's low frequency behavior is well controlled, preventing issues such as boomy bass or uneven energy distribution across the listening area. We also provide detailed pressure maps of the room at low frequencies, which are particularly useful when measuring the room, either when it's empty or after treatments have been applied. These maps help identify pressure nodes and areas where modal behavior is most preeminent. Occasionally, you might encounter unexpected results during measurements, and these pressure maps can be helpful to pinpoint the root of the problems, making it easier to address specific issues. It's an insightful way to visualize pressure distribution and understand where and how the most significant modes occur given the actual room setup. So this concludes our reports, and after more than 4 years of developing these documents and refining the process of building rooms using these algorithms, I'm very pleased to share that we've worked on over 100 projects, from which dozens have already been built, finalized, measured, and listened to, which is a great achievement for us. Here I've selected 7 projects that we'll take a brief look at, with a few of them being highlighted in more detail later in the presentation. First, let's take a brief look at the low frequency response of these 7 rooms and how well the measurements align with the simulations. So on the left, we have the measured and simulated responses for each room, and on the right, the error between the 2 curves. This is a narrow band analysis showing the results at 1 Hz resolution, so it's worth noting that in general, we are staying within a plus or minus 10 dB margin, and the overall behavior of the curves is well matched. However, we do see some larger deviations, particularly around narrow peaks that are misaligned by a few hertz. And despite this, the general trends and behavior of the low frequency response seem to be well captured by the simulations. Now let's take a look at the reverberation time for the same 7 rooms, comparing simulated versus measured in the same format. So here we generally stay within a 0.1 second margin, which might seem small, but for critical listening rooms, where the recommended values are as low as 0.2 or 0.3 seconds, a 0.1 second difference can be really significant. An interesting trend to note here is that all of the rooms show lower measured reverberation times in the 125 to 500 Hz range compared to the simulations. And one likely explanation is that we don't always have full details about the furniture during the project phase, so it is typically not included in the simulations. And considering this and the fact that we are on the lower frequency limit of ray tracing might explain some of the deviations observed in the measured results, but other than that, the simulations show a good level of accuracy for higher frequencies. Out of the 7 rooms, I've selected 3 projects of different room types for us to explore in more detail. So the first one of them, representing a commercial control room, is Ruboye Studio A. And this project is particularly interesting because the room serves multiple functions. It's a mixing studio for both stereo and immersive audio, but the same space also doubles as a live recording room. And additionally, it can accommodate more than 16 students seated at the rear of the room during mixing classes, making having a consistent acoustic response throughout the room especially critical. One of the most unique aspects of this room is how the console literally disappears, because the large console sits on an elevated platform, which lowers the console into the floor when it's not in use, and the top of the platform is also perforated. So when the console is raised, it acts as a low-frequency resonator, and when the console is lowered, it frees up space to transform the room into a live recording space that uses the auxiliary Studio B as the control room. This room also features a 5 subwoofer array, so in addition to the 2 in-wall subs mounted below the large speakers on the front wall, there are 3 additional subs positioned in the ceiling, to the left, right, and at the rear of the room. This configuration creates a very even low-frequency distribution up to 80 Hz throughout the center and the back areas, ensuring that all the students experience the same low-end content as the mix position. Here we can see an animation showing the pressure distribution using 3 different speaker setups. To the left, only the main system is active. In the center, just the 2 subwoofers below the main system are running. And to the right, all 5 subwoofers are working together. For Studio A, here is the low frequency response comparison. In the top row, we have the measurement and simulation curves, and below that is the error. We are analyzing the low frequency response for the left and right large speakers that are mounted in the wall. The response shows a great match, even though, as we discussed earlier, we don't get a one-to-one match for each individual frequency. And considering the necessary simplifications that are made in the acoustic model, in addition to the lack of several aesthetic elements, this level of alignment is really exciting to see, and it highlights the reliability and importance of the simulation framework. And in the same format, we can now see the reverberation time for Studio A, both simulated and measured. As mentioned earlier, the results are generally within the 0.1 second range, with the largest differences occurring between 125 and 500 Hz, likely due to the presence of furniture, which was mostly unaccounted for in the simulation. And finally, we have the full band temporal decay, both simulated and measured for the left and right in-wall speakers at the mix position. While the colors might differ slightly, making a direct visual comparison challenging, the overall behavior is quite similar, and there are clear resemblances in the decay patterns between the two. Studio A is a commercial recording studio built entirely from scratch to meet very specific standards. And now I would like to present a different project, one that was built within an unusual residential space. This was an existing room that we adapted into our studio for both mixing and live recordings. And what makes this project interesting is that we didn't have full control over the room's original architecture, including the walls and their construction. We also didn't have detailed knowledge of all the architectural elements, like the cabinets and windows. And despite these challenges, it's fascinating to see how the simulations and measurements compare in this context, given the complexity of working with pre-existing conditions. For this project, I want to focus more on the low frequency response, as this is where we typically see the most noticeable differences due to room boundaries like the walls and ceiling, especially when we don't have precise information about their construction. Despite these unknowns, the general behavior of the low frequency curves matches generally well. However, we do see some higher error values, sometimes reaching up to 30 dB, particularly at sharp peaks that are misaligned by a few hertz, which naturally leads to larger errors. But when looking at the broader trend of the curve, the overall behavior remains quite similar. This level of accuracy still provides enough confidence to make solid decisions during the project phase, even for simple, everyday, real-world rooms, which is really nice to know. Still focusing on residential projects, I would like to highlight this room for similar reasons. In this case, we have a more simplified speaker setup, as this is a hi-fi listening room, so it only features left and right speakers and amplifiers with no additional subs or digital signal processing. Other than the rear of the room, the space is fully symmetric, and since these are hi-fi speakers, we have very limited information on their directivity, which makes it interesting to see how the simulations will compare with all of these considerations stacked. Here is the low frequency response for the left and right speakers, both isolated and combined at the couch position. Once again, the overall behavior of the curve is similar, although we do see larger deviations for the right speaker, despite the room being fully symmetric. A key factor here is the lack of detailed data for accurately modeling the speakers that are commonly used in small rooms like these hi-fi speakers. In particular, we don't always have precise information on aspects like crossover frequencies or directivity patterns, which are usually more readily available for larger line array systems. And this makes it challenging to predict exactly how the speakers interact with the room, possibly leading to some of the discrepancies we observe. And here we have the full band frequency response comparison between the left and right speakers. We are comparing the measurements using our combined low frequency and mid to high frequency simulations. And here the discrepancy around 120 Hz becomes more apparent, where the left speaker seems to align better with the measurements, while the right speaker shows a larger deviation. It's important to note here that we are using 1/24 octave smoothing for this case, which will give us a cleaner view of the frequency response across the frequency spectrum. And despite the differences around specific frequencies, the general trend of the response is well captured. And lastly, we have the full band temporal decay calculated from our combined simulation and the in-room measurements. Here, in addition, I've also included a prediction of the RT60 using a frequency domain technique, and up until 200 Hz, where we are using the wave-based method, the matching reverberation time is quite accurate. However, as we move into the mid and high frequency range, where we are using ray tracing, and we rely on the minimum phase transform techniques to generate the actual impulse response, we can observe a higher baseline of reverberation time due to the noise floor introduced by that minimum phase transformation, as I mentioned earlier when describing ray tracing. So this concludes our presentation. I thank you very much for staying with us this long, and I invite you to check our website and learn more about us and our process. If you have any questions, feel free to reach out at info@rediacoustics.com and we'll be more than happy to answer. So yeah, until next time.